let's say you have these moving charges, then what is going to happen is there will be a field generated around it, and that field is called as the magnetic field. Okay, so what will happen is whenever you put the charges in motion, there will be a magnetic field generated around. So to keep it simple, wherever you have charge, so when you talk about a charge which is at rest or motion, when you see this word charge, the first thing that should come to your mind is electric field. Okay. So in addition to this electric field, let's say these charges are put in motion, right? So if you see the word charges in motion, then the first thing that should come to your mind is magnetic field. So you can ask me a question, when the charges are in motion, is there going to be no electric field? I didn't say that. Electric field will be there. In addition to that, you will also have magnetic field, but the reverse will not happen. Meaning, if you have charges, but if they are at rest, there will be no magnetic field, but there will definitely be electric field present around it. Is the point here? So this is going to be the introduction. Okay? So make a note of this. Done with this? Yeah. Shall we proceed? So the next concept that we are supposed to see is Biot-Savart law. Okay. So there were two French physicists. Okay. So it is a combined law. Unlike Coulomb's law, it is not proposed by one person, it was proposed by two people. So the question is, we understood that when there is a charge flowing in a particular surrounding, there is going to be magnetic field around, right? So mostly when you talk about the charges that are moving, you talk about an electric conductor. You talk about a conductor, right? So that is the best medium for you to carry the charges. So this Biot-Savart law mainly speaks about how to calculate the amount of magnetic field due to current carrying conductors. So this law will actually help us to calculate the exact value of magnetic field generated due to a current carrying conductor at different locations. So there are certain parameters on which the magnetic field depends on. That's what we are going to see now. So if I take a current carrying conductor like this, let's say there is a current which is flowing from bottom to the top. Let me say this is I. Okay. So first thing is, they did not speak about the current that, sorry, they did not speak about the magnetic field that can directly be calculated from the total conductor. But what they did is, the conductor was divided into infinitesimally small elements. Okay. So they broke it into many such small elements. Let's consider one such element dl out of. Now our interest is, due to this current carrying element. So try to understand, I'm using two words here. First word that I used is current carrying conductor. When I say conductor, I'm talking about the whole conductor. Whereas when I say current carrying element, I'm talking only about a small part that is considered on the conductor. So due to this current carrying element, if I take a point P here, let's say, which is at a distance R from it. R from whom? From the current carrying element. Okay. And let's say this is treated like a vector. And I say that the angle between the current carrying element and this R vector is theta. Then the parameters on which the magnetic field at this point is dependent is given as, first thing, magnetic field at any point. The symbol used for magnetic field is B. The symbol used for magnetic field is B. But here, since you're not calculating due to the whole conductor, you're calculating only due to a small element, the magnetic field will not be treated as B itself, rather it will be treated as dB. Because due to this element, the magnetic field at that point will also be small. Right? So if I want for the whole conductor, what am I supposed to do? I need to follow integration. Is that clear? So the magnetic field due to the small current carrying element. So dB is the magnetic field due to the current carrying element dl. Okay. So it is given like this. dB is directly proportional to the magnitude of current flowing through that element. It is directly proportional to the length of the current carrying element. Okay. It is directly proportional to sine of the angle between the current carrying element and the distance. So it is sine of that angle. Okay. And it is inversely proportional to the square of the distance from the current carrying element to the point where you are interested to calculate the magnetic field. Okay. So dB depends on four parameters. What is it? One is the current flowing through the conductor. So current flowing through the conductor will be the same current flowing through the small element dl, because all these dls are connected in series. All these dls sum up to give you the whole conductor length, right? So the current through this dl will be the same current. That is why I wrote it as I here. dB is directly proportional to I. dB is directly proportional to dl. It is proportional to the sine of the angle between the current carrying element and the distance, the distance vector, okay, taken from the current carrying element towards the point P. So you observe the way I have considered it. I've taken it from the current carrying element towards the point where you are interested to calculate the field, and it is inversely proportional to the square of the distance from the current carrying element to the point. So when I combine everything and write, we get dB is directly proportional to I into dl. I'll treat it as one element, I into dl into sine theta, the whole divided by r square. Right? So since you have proportionality, we need to remove it and introduce a proportionality constant. So from this, what we will do is, after we remove the proportionality constant, it becomes equal to, you write mu naught divided by 4 pi into the same thing, ideal sine theta divided by r square, where this mu naught by 4 pi is going to take a value of 10 power minus 7. It takes a value of 10 power minus 7. I'll tell you what is the unit of it. And the second point that you need to know is mu naught is called as the permeability of free space. So epsilon naught is called as the permittivity of free space. Here it is called as permeability of free space. So it's called permeability of free space. Okay. Now, having said this, I told you that the symbol used for magnetic field is B, and the unit used for measuring the magnetic field in SI system is given as T, which is Tesla. Okay. So Tesla is the name of a scientist, so you use capital T. Okay. So if this is going to be capital T, tell me what is going to be the unit of mu naught by 4 pi. So capital T, that is Tesla. This will go to the other side as meter square, right? Tesla, I'll write it separately. Tesla meter square divided by, this comes to the denominator as ampere into meter. And sine theta does not have any unit. So this meter will cancel this meter square once. So you're left out with Tesla meter per ampere. So this mu naught by 4 pi takes a value of 10 power minus 7 and its unit is given as Tesla meter per ampere. Okay. So this is all about Biot-Savart law. Derivation is not needed. Okay, there is no derivation or anything. This law is stated. We are going to take this and apply it in different parts of this chapter. I hope it is clear, no? So make a note of it. Done with this? Go. Ideal. No. Combine but ideal sin theta divided by r square. This whole thing is multiplied with mu naught by 4 pi. இது ஆமா yeah it is dl. இதுவா இதுதான் yeah dl. Done? Shall I proceed? Okay. No. The next question that we need to understand is, okay. So the next question that we are supposed to understand is, when I talk about electric field, what kind of a physical quantity is it? Is it a scalar or a vector? So electric field is a vector quantity. And how is it directed? It is always from positive to the negative charge, and it does not form any closed loop. It starts from positive, ends at negative. Now, when it comes to the question of this field, that is magnetic field, is it a scalar quantity or a vector quantity? So this is going to be a vector quantity. So here also you have direction associated. What is the direction for it? If I take a magnet, for instance, okay. So when I talk about magnet, there are two types of magnet which we can speak about. One is a permanent magnet and the second is a temporary magnet. So permanent magnets are the ones which are bar magnets, horseshoe magnets, right? All those things are permanent magnet because they do not rely on the current to generate the magnetism. They always have magnetism associated with them. Whereas when you talk about temporary magnet, they are electromagnets. So what is the concept telling us? The concept says that when current is passed through a conductor, magnetic field is generated. Then what about the situation when current is not there? Then obviously there is no magnetic field around it, right? So these magnets are temporary magnets, okay? Now, they both can be connected because they both are generating the same thing, the same phenomenon, which is magnetism. So I'll try to relate both and tell you. So when you talk about a permanent magnet, which every one of you have seen, it has a north pole and a south pole. I've taken a simple bar magnet, okay? So how is the magnetic field going to be in this scenario? It is going to be from the north pole towards the south pole outside the magnet, whereas inside it is going to be from south to north. Unlike electric fields, they do not, unlike electric fields, they form closed loops, right? So outside it is going to be from north to south and inside it is from south to north. So when you talk about a permanent magnet to have this kind of magnetic field direction, then there should be something with respect to the temporary magnets as well, right? So there needs to be a way for us to find how the direction of magnetic field is associated with it, right? So for that, what are we going to use? We are going to use right hand thumb rule, right? So which everybody knows. You know this law. Suppose I take this to be the conductor, right? And the current direction of current is upward. So right hand thumb rule, first thing we need to understand, there are different rules you would study. One is right hand thumb rule, Fleming's right hand rule. So you should not get confused because both are speaking about right hand only. So here the name is suggesting as right hand thumb rule, meaning I need to use the thumb of my right hand and figure out something. So what am I going to do is, we will take the thumb of the right hand and place it in the direction of current, right? After that, you need to curl the fingers of your right hand as if you're going to hold the conductor, right? I repeat it. Take your right hand, place the thumb of your right hand in the direction of current and curl the fingers around the conductor as if you're going to hold it. When you do this, the direction in which the fingers are getting curled will give you the direction of magnetic field. Because we know that magnetic field forms a closed loop. So I can take this complete loop also. So when I take this to be a straight current carrying conductor, it's going to be a set of concentric circles around it. Right? It should have definitely seen in your lower grades. So what I'm saying is, if I take a conductor, if this is how the direction is given, so I took this as a straight conductor, not necessary that every conductor needs to be straight, even if it is bent. All that you need to do is find out the direction in which the current is there. In that direction, place your thumb and curl the fingers as if you're going to hold the conductor. So it's very simple. Okay. So when you curl the fingers on the right side of this conductor, my fingers are going and touching the board. Right? Meaning this board is receiving the magnetic fields. Am I right? So here what I can say is the magnetic field is into the plane. So for representing into the plane, you use an into mark and a circle around it. Okay, this is called as into the plane. And I want to stress on one point here. Into the plane is not used only for magnetic field. It can be used for any physical quantity. If you put an into mark and a circle around it, you're trying to tell someone that this particular physical quantity is into the plane. And with respect to magnetic field, one advantage is if you're able to find what is going to happen with respect to the conductor on one side, on the other side, it will exactly be the opposite. Why is it so? Because if I bring this conductor out, if I keep my thumb like this side is going into the plane. So other side, it is coming out of the plane. So for out of the plane, you will put a dot and a circle around it. So when a dot and a circle around it is put, it is understood that you're talking about out of plane. I hope it is clear. Right? So just to summarize, we'll come from the beginning. What did we discuss? Talk about right hand thumb rule. We need to take the right hand and put the thumb of your right hand in which direction? In the direction of current. What is the second step? After that, curl the fingers of your right hand as if you're holding the conductor. So the direction in which the fingers are curled gives you the direction of magnetic field due to that particular conductor. Is that clear? Yes. And lastly, what did I say? If you put an into mark and a circle around it, that physical quantity is directed into the plane. A dot with a circle around it, the physical quantity is out of the plane. So to be more precise, mostly what you will do is, this is like this, no, you're looking at the whiteboard. Mostly you will be looking at your paper like this, right? This is how you write in your exams and everything. When you have like this, when you put into plane, into mark and a circle around it, have this in your mind. Like that particular physical quantity is away from you. So have this in your mind because in 6th chapter, I'll be connecting to this. What did I say? Into the plane means that physical quantity is away from you because we are facing it. See, now I'm turning towards you and speaking. But actually, when you are facing it, what is happening? It is away from you. Here it is towards you. You're able to understand? So going forward, I'll be using this language. Okay. So make a note of. No. See, this resultant force, you don't worry about it. This can be used to find the direction of force also. See, all these things come from only one concept. Can you tell me which concept of vectors is actually helping you to find these directions? Everything is cross product. Everything. Slow down. Cross product. Okay. பொறுமையா பேசு. Shall I proceed? Yeah. So listen. Listen. See, since we told that magnetic field is a vector quantity, Biot-Savart law helped us to find the magnetic field, intensity of the magnetic field due to a small current carrying element at a distance r from it. Right. Now the next question is, how can I combine the concept of intensity and the right hand thumb rule and bring a vector form to this Biot-Savart? Am I clear? So that's what we are going to see. Okay. Listen to this carefully. If I take a current carrying element dl, I'm taking the same diagram again. If I take a point P here, and if I take this distance to be r, right? So from dl towards point P, this is going to be the vector. Okay. So here, the first point to be noted is whenever you want to apply this so-called Biot-Savart law in vector form, the first point that you need to register in your mind is whenever you speak about distance as a vector, there is always two possibilities. So when I talk about a vector, I can take the arrow mark in any direction I want. In this case, what I did is I took it from the current carrying element towards the point P. We could have taken it in the reverse also, from point P towards the current carrying element. But that is not how it is taken. Okay, so to put it simple, whenever you talk about the distance vector, you need to ensure that the current carrying element is the initial point. That's the first point to be noted. So what did I say? Current carrying element should be what? Should be the initial point for whom? Initial point for r vector. Okay, so this can be written as r vector. Secondly, this is the direction of current and this is dl. Here there is a tricky part. Current has direction, but it's not a vector. dl has a length, but no direction. Are you able to understand? It's a challenge, no? Current has direction, but no, it's not a vector. dl has only magnitude, but no direction. So what should we do is we should combine both. So that is why you write everything as ideal. And when you write it as ideal vector, this ideal vector will take the direction of current itself. Makes sense? Right? So this ideal is treated as one vector quantity as a whole. Right? I is neither a vector, dl is not a vector. So what we did is you wrote it as dl vector, right? And second is r vector. Now we will see the Biot-Savart law in scalar form. So dB is equal to mu naught divided by 4 pi ideal sin theta. Okay, 1 minute. I use small I, no? Yeah. Ideal sin theta, the whole divided by r square. Right. Now I have ideal and sin theta. Right. Since I want to write this in the vector form, what I need to do is I need to bring that sin theta into some operation. So whenever I think of sin theta, the first operation that comes to my mind is cross product of vectors. So if I have to write as cross product, in the numerator, I have only one vector quantity, which is ideal. So I don't have r. For that, what we will do is we'll multiply with r and divide with r. Okay. So this will become mu naught by 4 pi, the whole divided by r cube, into ideal into r into sin theta. Right? Ideal into r into sin theta. So first vector into second vector into sin theta. Again, there is a challenge with cross product. Thing is, a vector cross b vector is not the same as b vector cross a vector. So I don't know whether I should write it as ideal cross R or R cross ideal. Okay, one minute. So I don't know whether I should write it as ideal cross R or R cross ideal. So what should I do? That's where the right hand thumb rule will save us. Okay. So we will connect two things now. Listen to this carefully. I'll be connecting the concept of cross product of vectors, how to apply right hand thumb rule for cross product, and how to apply right hand thumb rule for current carrying conductor. So when we talk about cross product of vectors, if I take this to be A and this to be B, right? If I write A vector cross B vector, okay? Listen to this carefully. When I write A vector cross B vector, you should always keep the second vector fixed. So B vector is fixed. First vector should be rotated towards the second vector in the shortest direction possible. So if this is B vector, this is A vector, I need to rotate A vector towards B in the shortest direction possible. Here it is going to be anti-clockwise. So there you take your right hand, first you will curl the fingers and then extend the thumb. What do? You first curl the fingers and then extend the thumb. The extended direction of the thumb will give you the direction of resultant. Am I right? So A vector cross B vector, if you take it in this way, in this scenario, what is happening is, since anti-clockwise direction, what is the direction of resultant? If I call A vector cross B vector as C, what is the direction of C vector? Is it into the plane or out of the plane? Out of the plane. So C vector is with a dot and a circle around it. Right? Similarly, if I take B cross A, what should I do? I should keep the second vector fixed, come the first vector, take the turn towards second vector in shortest direction possible. So here B cross A will be negative of C vector. It is into the plane. That part I am not explaining. Is the point clear? Now, having said this, how do I check which one should I apply? Should I write ideal cross R vector or R vector cross ideal vector? So if you do either of them and check, you should get the answer. Now see, this is with respect to cross product. Now, what is right hand thumb rule with respect to the current carrying conductor telling us? What is right hand thumb rule with respect to current carrying conductor telling us? Now I am going to concentrate only on this conductor. Okay. So since the current is in upward direction, what is the direction of magnetic field due to this element at point P? Is it into the plane or out of the plane? So due to current carrying conductor, here you will first place the thumb and then curl the fingers. In cross product, what you do? First you will curl the fingers and then extend the thumb. So it's exactly the reverse operation, but both are right hand thumb rule. Okay. So here what is happening? Extend the thumb and curl the fingers. So at point P, it is into the plane, means it is away from you. Right. So what operation should I perform? So if you see, for you to get into the plane at this point, you need to perform the operation of ideal vector cross R vector and not R vector cross ideal vector. Because what did I say? You need to curl the fingers of your right hand. So again, I'm coming back to cross product. For cross product, first what will you do? You will curl the fingers, extend the thumb. Okay. So when I do that operation, what should be the direction in which my thumb should be facing at that time? It should be into the plane. So observe, if I do ideal cross R, so when I told you do cross product, you should fix the position of second vector or first vector? Second. So here who is the second vector? R vector. So this is R vector. This is ideal vector. So from ideal vector, I need to turn towards R vector in the shortest direction possible. When I take a clockwise turn, then it tells me that take your right hand, curl the fingers of your right hand in clockwise direction and point the thumb, it will be into the plane. So the cross product and right hand thumb rule are matching. Under what scenario? Only when you do ideal cross R. Suppose you do R cross ideal, what should happen? You should fix the direction of ideal vector, and from R vector, you need to take a turn towards ideal vector, which is anti-clockwise. So when you extend it, it is out of the plane. So here it is actually into the plane. So both cannot contradict. That is why when you write the expression for magnetic field in vector form, this has to be remembered. What is it? It is ideal cross R vector, and second point to be remembered is denominator is not R square, rather it is R cube. Is that point clear? So if this question, this can be asked directly in your MCQ also. So they'll give you two options to confuse you. Actually, 4 questions can be framed from this itself. Now itself, I'll tell you how they can frame. dB vector mu naught by 4 pi will be fixed. First option will be ideal cross R by R square. Second option will be ideal cross R by R cube. Third option will be R cross ideal by R cube. Fourth will be R cross ideal by R square. Here, so which one is right? Ideal cross R should be first thing in the numerator and R cube in the denominator, right? So this is the expression for magnetic field due to Bayes' magnetic field using Bayes-Savart law and being represented in vector form. Okay, so make a note of it. தெரியாது அந்த வயர் எடுத்துக்கோ இந்த வயர் எடுத்துக்கோ தின் வயர் தானே இது இப்போ இது as per this diagram what is the direction of current ஸோ இப்படி தானே பார்க்குறேன் ஸோ எப்படி தெரியுது உனக்கு மேலே தானே தெரியுது எனக்கு இங்கேருந்து பார்த்தாலும் மேலே தான் தெரியுது புரியுதா ஸோ இப்படி பார்த்தா யூஆர் சீயிங் அப்வர்ட்ஸ் ரைட் திஸ் இஸ் யூஆர் ஃபேஸிங் சரி இப்படி திரும்பி காட்டுறேன் எப்படி இருக்கு மேலே தானே இருக்கு will not change. You should see only from front or back. You will not go to the other side and see. அப்படி பார்க்க கூடாது. The direction is fixed. The only thing that will change is magnetic field. Magnetic field direction change ஆகும். அதாவது நீ இப்படி பார்த்தா magnetic field direction இங்க வந்து into the plane. பின்னாடி போய் பார்த்தா it will be towards out of the plane. Yeah. It will be out of the plane. You try and see, no, it will still work. I gave only for one scenario. You can try and see it should work. You understood both the logics, no? You understood cross product, you understood right hand thumb rule. You know to connect them. Connect and see. Is there anyone confused with this? Clear? So by Monday at least your assembly things will be over. Monday முடிஞ்சிரல முடியாதா 11th உங்களுது முடிஞ்சிருச்சு அதாங்க because next one there is an important derivation. It will take 25 minutes for me to explain. Monday, I don't want you all to miss it. Any of your friends who missed the class here today? So if at all you have friends who missed the class, it's your job to teach them. Only then you will have clarity. In the chapter, the more you teach, the more you can learn. Trust me on that. It's up to you then. I'm not asking you to give a seminar standing here. Explain it to your friends. The more you teach, the more you will understand. Clear? Okay. See, in your 10th grade, you would have learned about different shapes of conductors, right? Right. They would have asked you to draw the magnetic field due to a straight current carrying conductor, circular current carrying conductor, solenoid. All those things were there. So based on that concept, I'll just show you what is supposed to happen. We need to calculate the magnetic field due to a current carrying conductor of finite length. Okay. So you have a straight current carrying conductor, let's say finite length. Due to that conductor, the magnetic field at a point is what we need to calculate, for which we'll be using Biot-Savart law in the scalar form. See, mostly vector form is not used. Okay. As long, unless in the problem they've given you the vector notations itself, you're not going to use it. Most of the cases it will be scalar part only. But it's important for you to know that. Okay. So when we use the scalar part, we will first, I'll give you the outline of what we are going to do. So first we'll calculate due to a small current carrying element. That's what Biot-Savart law says, right? Due to that small current carrying element, we'll calculate what is the magnetic field at point P. Then we need to integrate. So to put it simple, these are the two steps we need to follow. But the process is slightly lengthy because I have to explain integration also to you. As of now, you don't have knowledge to handle it. No? What will happen is you will have 2-3 variables. You have to convert it to one variable. It's simple. It might sound complicated when I'm talking, but it's simple. As we progress, you'll understand. But at least 25 minutes to 30 minutes to explain this derivation alone. Next class, I'll start this. So Monday, we'll be starting with this. As I told you, those who missed the class, go and help. So I'm telling seriously, go and help them. You will learn better. You explain to them. If you have confusion, reach out to me. Okay. So any other questions? That's it. Wind up. We'll wind up. Sorry, ma. Previous slide. Iduva. Here.